So yeah, my name is Chris Edelmaier. I'm a relatively new software engineer in CCB, and today I'm going to be talking to you about our efforts to develop sort of the next generation of one of our simulation frameworks named Lens, and some of the lessons that we learned from the first Lens, and what we're trying to do better that hopefully can be takeaways for many of you going forward when developing what are hopefully long-lived software frameworks. So one of the first questions on everyone's mind should be, what is a lens? So a lens stands for a living ensemble simulator. It is a software package that was written here in CCB, although it went by other names before in various incarnations, that is essentially for simulating some number of rigid body objects in space with, say, dynamic springs that can link to objects and unlink from objects. Now, this is important because it essentially breaks our problem into two steps. This is molecular dynamics type code that not only does the rigid body collisions with each other, but it can also do dynamic linking and unlinking of objects inside the program. So this means that you have some sort of state changes going on inside of the framework. So this is an example movie of one of the more recent versions of a lens, where this is supposed to be modeling actin ring formation inside some sort of spherical geometry. So we have flexible filaments that are linking to each other with dynamic springs that are coming on and off the system, and we can actually simulate these sort of large systems forming in the bulk. Now, one of the interesting things to point out here is that this is hundreds of thousands of degrees of freedom in this system. So not only for a lens do we have to deal with sort of this multi-component model where, let's say, we're doing molecular dynamics and then some sort of state change dynamics, you also have to keep track of a lot of data and do this in some sort of performant manner across multiple nodes if possible, or using, let's say, all the computing power you have access to, which may or may not include GPUs. So again, this is sort of just an example of one of these multi-body systems that we're working with, but let's simplify it down and say that, okay, we have something that's just two rods. They may or may not have springs connecting them in different places. So for the purpose of what we're talking about, we have these objects, and you can write it down essentially as a graph of where the interactions actually come from. So you have two rods, you have springs that interact with them. Maybe you have a spring that isn't interacting with them. And of course, these sort of arrows can change between the states. So what can you do with a lens? So, well, you can do cytoskeletal active matter. So this is one of the projects that was used where you can get clustering of filaments in some sort of different geometries. You can also use sort of the same code to model bacterial growth colonies, where you have a rod that's growing, and at some point it divides into two rods and they keep bouncing into each other. Maybe it undergoes thermal fluctuation, maybe it doesn't. And you can have sort of bacterial colonies growing. Or maybe you want to model colloidal suspensions in a fluid. And so you have rotamers and you're sitting down, and these are all in some sort of geometry with a fluid background. And you want to do all of these things. So this is what a lens is supposed to be able to do. But I've already sort of told you a lie, is that a lens is maybe the group of pieces of software that can do all of these things, but it isn't actually the piece of software that does all of these things. And this sort of gets into the problems with the first version of this code. So what we wanted a lens to look like, and I'll switch back and forth between saying a lens and a lens, and I can never decide which I like. The initial design was that, okay, we want to do some sort of particle dynamics. Well, looking around online, you come up with this package, which is, I just completely spaced the name. It's FDPS, I forget. Thank you. It's in the note slide. Framework for Developing Particle Simulators. It's a framework, it sits online, and it's a way to keep track of all the data in your system. Okay, so we have some library that already exists that does some of the data bookkeeping we're interested in. So we build something on top of it that does the extra pieces of the computation that we need that are physics independent. So this is things like, okay, I want to use MPI to do communication between different processes. Maybe I want to use OpenMP to do thread-based parallelism. If I'm doing MPI already, I can scale this across multiple nodes. Great. Just have to make sure that everything talks to everything else okay. And then in the end, you can put your physics or domain-specific problems in a lens itself, which then sits on top of Sim Toolbox, which then sits on top of FDPS, okay? And then you can do all of these cool problems. But as I've already told you, this is a lie. So what really winds up happening is that, well, because of how Sim Toolbox is built and some of the problems inherent in how it was designed and some of the weaknesses of FDPS, you wind up with something that looks a lot more like this to begin with, which is the, okay, well, these three different projects are actually forks of the initial same repository, where we have, okay, there's a lens, strictly speaking, over there, and then we have one that's, okay, to do the hydrodynamics with the spheres, there are some things that are different. So we forked the repository and it grew into its own project. And then Cell Simulator, well, we don't really need to know about fluid, so, well, let's just have something that just grows these rods and allows them to collide with each other. It doesn't even need to know about springs necessarily, okay? The problem is, this is also a lie, as I've drawn it here. What really happened is this. So I think we can begin to see the problem here. So we're all at least still built on this FDPS code that underlies the system. That's the basic data representation. But then we have 4 different versions of Sim Toolbox lying around that do different things. And then all of these projects, and I've included a couple others here, there are more than this. I don't know if we have a countable number of forks of this repository. It depends if you count different private versions of the repository on people's laptops as different forks or not. Anyway, there's like 17 or something, probably more. 17, there's n. So the problem here was that while we are built on the same baseline code, the original idea for Sim Toolbox as a bookkeeping mechanism has some weaknesses. And so this is a good demonstration of what is called code fracture, which is that whatever your underlying code was doing isn't flexible enough to support all the different things you want to do with it. So if you're trying to write a generalized framework for something, you immediately run into this problem where essentially everyone that was given the original Sim Toolbox wound up with many different versions of this code. And so you wind up with like this sort of huge splatter of repositories and projects all over the place. And then you come through and say, well, what is a lens? How do we combine everything back down into a single project? Can we even do that? Like, what would be even necessary to recombine all these projects back down together into one thing? Yeah.
Is Sim Toolbox something that you or Flatiron people or this list of collaborators wrote?
Yes. So the original Sim Toolbox was Wen wrote it, built on top of FDPS. So this was before my time. But as I understood it, was looking around for a bookkeeping mechanism to keep track of your data when you want to do these highly parallelized computations. Found one that, again, I'll go into the weaknesses here in a moment, but he decided to base Sim Toolbox on FDPS.
Yeah, great. Okay, and then that was the thing that fractured.
And then Sim Toolbox is really the thing that fractured once we started looking at different projects that you wanted to do with it that didn't necessarily share a lot of the pieces. But anyway, if we come back to what happened with a lens, like, it's really good. And I like using this comic that I got from Dan. I saw you put it in a presentation once. I think so. I think it was in a Daedalus presentation. Anyway, it was Keaton? Okay. Okay, but a lens is really good at a couple of these problems, but we really have like 17 of these different hammers, all for nail-shaped problems. So the problem with a lens is that when you have these code fractures, you have a sort of loss of version control, like I said. If I have 17 of these things running around, keeping track of all of the different changes, and if I can merge them back together at some level, effectively becomes impossible. When it was first developed, there wasn't a good sense of what the end goal of the project was, other than it was sort of showing off this constraint-based optimization algorithm to do the particle motion. And then a lot of the other stuff came along just because of the choice of FDPS as a underlying data representation. Speaking of FDPS, this is kind of a problem. So it was alive as of 2018 when this choice was made, but I don't think it's been updated since then. So it's effectively abandonware as well. No one's dealing with it anymore. I think it was originally astrophysical calculations was what it was designed for. That's kind of a problem if you have something built on a project that's not maintained anymore. A lens also suffers from the fact that because of all these fractures, you have sparse documentation, and you also have sparse testing. So we're going to get into why testing is good here in a few slides. But basically, without testing, you have no way of knowing if a change you made broke everything else. And especially with research code, you run into problems where you make a change, something broke, but because you don't have tests, maybe you don't catch it until 5 weeks later, where suddenly you're like, oh, this shouldn't be this way. Where did this change happen without any sort of good testing? So you have lack of trust in the software system you're dealing with. You have these regressions where something broke and you don't know about it. It can also lead to slow development, both the documentation and testing, because you're always worried about these issues, or maybe you don't know how the API functions. So the code fracture itself, sort of the first part that I want to go over is how many of you have written code that looks like this? You have something that's called spheres.cpp, and then you copy it into spheres_v1.cpp to make modifications. No, wait, you need to have a new version, spheres v2. No, wait, this one. No, wait, this one, really this time, but maybe you misspelled it, so your makefile has problems. This one doesn't compile. Not sure why we threw a question mark in the file name, but sure. And then, oh yeah, it was actually v1, but final.cpp. All of us are guilty of this, I'm pretty sure. I know I am. If you go look at this exact presentation, we're on FWAM v5. So I am guilty of this right now. You shouldn't do this. Git exists for a reason. We'll get into that in a moment. So this was one of the problems with all of these code fractures, is things begin to look like this. One of the other main problems was that because we were based on FDPS, we had problems with having extendable heterogeneous data structures. And this is a good example of what happens. So let's say I have a sphere class, a sphere particle in my system that I want to do something to. So I store its position and radius, and then I make some collection of these particles in the system, 100,000 of these things. Okay, cool. Let's say now that I want a different kind of sphere that maybe has an orientation associated with it. This is one way to achieve that, is I go into the base code for the entire system, I make the modification to sphere, and I stick an orientation variable in there. So everyone now has to carry this with them. That is very bad, because you're forcing everyone to depend on things that they may or may not care about. So here, this is a problem because I've suddenly stuck this new variable in everywhere. But you can imagine, as you have a lot of heterogeneous data in your system, this problem just gets worse and worse. If you have rods and ellipsoids and triangles, and maybe you have springs that sometimes exist or sometimes don't, this piles up very, very quickly. You wind up in a combinatorial nightmare. So literally, this is, you can go look in your textbook for CS. This is a inextensible design pattern, because to extend it, we have to actually make modifications to the base code. And this accounts for at least 4 of the fractures, but again, not sure how many it accounts for, because I don't know how many there are in total, really. Okay, so if we were going to redo this, we know that we need the ability to have extensible fields in the particles. We want the ability to be like, oh, I have a sphere of some type, and then maybe I have a rod that's just a completely different type. Maybe they share data, maybe they don't. That leads to another problem here, is that the way FDPS is set up, it wants homogeneous particle types. So if you hand it something, it's expecting everything to be a sphere or an object. So if you wanted spheres and rods, you can't really do that without making everything a rod. So you can't necessarily do anything other than this. You could hold 2 complete homogeneous systems together, and then you have to define all of the interactions between them. So that's also a problem. Okay? So that's sort of what had gone wrong. So how might we go about fixing this? And this is our current work into developing ALENS 2 effectively, which, okay, there were some choices made in ALENS that were problems. So effectively, this is a ground up rewrite of the entire thing. So if we were to start over, we want to be flexible. So we want to hold heterogeneous data in an efficient manner, hopefully parallelized across, say, many nodes and heterogeneous compute architectures. We want to be extensible. So this means that I'm not diving into the C++ code for sphere and modifying it directly. If I want a new type, I can create my own and inject it some way into the system. We want it to be performant on HPC systems. Again, I'm talking about hundreds of thousands of degrees of freedom, probably countable into the millions or 10 millions for some of the systems we're thinking about. So this really needs to be highly parallelized for a cluster architecture. It would be nice if we weren't built on a dead project. So hopefully choose something that's a little more lively or might live for slightly longer. So this is the idea, at least. Okay. So what we're going to do is, to solve that problem of versioning to begin with, we're going to use Git. So how many people here have used Git? Excellent. Okay. How many of you have used GitHub? Notice the quotation marks. So do you use Git as just a repository that you push and pull from and do merges to? Or have you used any of the internal features of GitHub, like project management and issue tracking? So this is just sort of a promo for, you should use GitHub, and you can use it as a version control system. You can also use it to do issue tracking. So these are just some test issues, like, create a CMake file to intake Monday, which we'll learn about in a moment, or figure out ALAN's 2 connection between projects and repositories. I especially like that issue. You can also do project management, which we're working on, which is designing, let's say, deliverables for a software project of what pieces do you want something to work and when do you want them. So these are just sort of examples of that we're attempting to flesh out right now. Okay, so we know what we're going to do. We're going to build this in Git, which, yeah, you should always do that for any project so you don't have this v50.cpp problem. Okay, how do we address this extensible heterogeneous data problem? So what heterogeneous data usually looks like is, okay, I have a system with spheres in it. They are defined by their center of mass position and a radius. I have rods in the system: center of mass position, orientation, radius, length, and ellipsoids. So just keep growing the number of things in the system, okay? And these are color-coded for a reason. One way to do this is you could use inheritance in C++, build all of your objects based on some sort of base object, and each one only has to know about itself, and you maintain a pointer to arrays of this base object. So you could store it like this. So we saw earlier from Steve the idea of a array of structures, and this is one way of handling this. But usually, if you try to store data for these large MD simulations this way, you immediately shoot yourself in the foot, because when you go to actually access these things for highly parallelized applications, you run into problems with grabbing the data. What node does the data sit on? You destroy memory locality. So it's very flexible, but this is very inefficient when you're actually trying to compute things. So instead, what we chose is to do the opposite, which Steve also brought up, which is the structure of arrays. So for sphere 1 and 2, we know that we have these variables, x1, and so we have their positions, we have their radii. And for the rods, some of the fields are actually shared. So if we had something that allowed us to say, oh, rod 3 and 4, they're their center of mass positions, they also have radii, but also then keep track of the orientation and length, that would be really good. And then you can also tack on ellipsoids here, where some of the underlying data structures might also be shared. Make sense thus far? So this allows you to essentially lay out everything as flat arrays that then you can do neat tricks with locality and making sure that nearby neighbors talk to each other. So this takes us into what Bryce spent a lot of time doing before I showed up here, which is MUNDY. So MUNDY stands for multi-body non-local dynamics. Hopefully I got that right. Yes, he's nodding. So the idea here is that a lot of what I just talked about for the heterogeneous extensible data structure already exists. So Sandia National Labs has the Trillanos ecosystem, which is this huge heavyweight thing that does a lot of different, it performs a lot of different computational tasks. One of the things that lives inside of it, though, is this STK mesh, which was originally used for finite element analysis to solve problems like, oh, I want to know how wind moves past a wind turbine, or like if I blow up this wall, how does it deform, or fire simulations. So it actually encodes this extensible heterogeneous data already that you can push things onto and off of this mesh, and it will handle putting the data on different nodes for you. So that's good. So that's what really gives us the extensibility, both for the problems of needing to add data to particles that, say, only we're interested in, but also how to keep track of multiple types of particles just by essentially assigning the data onto and off of the mesh. And this leads to a lack of a lot of the workarounds that existed in ALENs, where you had to maintain, let's say, different vectors of objects or copy interactions in different places to communicate back and forth. So it eliminates some of those workarounds. Bryce.
Why not use existing software like LAMP, SUNY, Blue, GROMACS?
So in many cases, those are really good. They are very fast. LAMPs, HUMDI, and GROMACS, if you go peek under the hood, they all are based off of point-like particles in almost every case. Sometimes they fake looking like rigid body particles, but in most cases, they aren't actually any sort of rigid body particles. Also, trying to extend those to different data types is very difficult. Also, one of the key steps for the things that we want ALENs to do is to be able to do these state changes of the system, which, depending on if you're in HUMDI or LAMPs, are very difficult to write. And you have to write your own, that you're injecting code or compiling against the base version of the library, and you have to recompile the whole project to be able to do that. I have seen it done in HUMDI once. It was not done terribly well, and it was horribly inefficient to do dynamic bonding on a GPU. But that is hopefully something that we can do instead. So there are problems with the performance, but like, this isn't to poo-poo on them too much. Some of them are blazingly fast. HUMDI is incredibly fast and can do large systems of particles, and it's pretty neat. I have other views on LAMPs. Oh, yes, Pilar.
Did you make any decisions on your programming languages and parallelization?
Yeah.
So I was asking if there were any decisions on changing programming languages or parallelization schemes.
So what we're doing right now for sort of task-based parallelism, we're using MPI. So okay, let me take a step back. We're using C and C++ because that's what the SDK mesh is in. The entire Trillanos package is a set of C, C++ libraries. I think there is a few Fortran things in there too. But it's essentially all in the C, C++ Fortran level of code. So we decided to program in C and C++ to also use, say, some of the advantages of templatized programming along with abstraction for inheritance to carry out some of the tricks for, especially for Mundi, for the bookkeeping, where you don't want to have to write a separate implementation for all of the different, let's say, methods that you want to use. Let's say that you have a whole bunch of different kernels, like a hydrodynamics kernel or an EM kernel and a Leonard-Jones one and a harmonic well and a wall and all of these things. It's a way to get away from that and do it in a nice way that still that natively compiles against Trillanos.
And what about CUDA?
So in theory, we are going to be CUDA compliant. So how we're going to get what we're going to do in that case is all of our kernel launches to actually carry out the computations. We're moving towards using Cocos to be able to do this, which allows you then to launch on either threads or on the GPU. But there are a couple key problems that we're missing right now for actually having the ability to do that. Mainly that so the SDK mesh, one of the things it gives you is a giant connectivity graph of your system. And this is how you determine locality of different objects. Adding and subtracting edges to that graph is done on the CPU right now. It is not necessarily done on the GPU yet. So I think, Bryce, you actually logged a request against Trillanos to add that, and they said no. So maybe we can convince them to add it, or we'll have to write our own possibly to do like one of the pieces that prevents us from being truly GPU compatible. Right now, we would be able to launch kernels on the GPU for some of our computations. And again, if we're doing 100,000 of them, maybe it's okay, but use the GPU as a coprocessor just to evaluate the kernels and then bring the data back and not have to, you pay the price in sending the data there and retrieving it rather than run the whole thing on the GPU. But we may be able to do that and still get a performance increase just because the number of particles on our system is large enough. We have to test it to figure it out. But that's that's the main problem with moving towards like a GPU solution at the moment. But effectively, essentially what we're going to do is say, oh, we're going to use Cocos to launch these kernels. Any other questions? Okay, cool. So Monday. Okay, so Bryce has been coding this up for a while, and we have some preliminary results in Sim Toolbox, which I showed you, which was the ALENS 1 version of this bookkeeping mechanism, and Monday, which is the ALENS 2 version. And again, this is supposed to be a library that is in fact domain unspecific, domain non-specific, to your problem. So it doesn't necessarily care about the physics of your system or what you're trying to do with it. It's bookkeeping and putting the data on all the different nodes that you want to talk to and retrieving it in some sort of consistent manner. So if you do performance analysis of Monday versus Sim Toolbox, you can write down what the speed up is in both cases. So this is just if I throw, good speed up is if I throw twice the processing power at the problem, does it run twice as fast? So in the case of Sim Toolbox, it had some issues with scaling performance as you threw more computing power at it, as opposed to Monday, which is now much better in terms of performance. Yes, it does. So perfect scaling, which is this line, is I throw twice the processing power at it, I get twice the speed. It does beat it sometimes. I guess I'm not supposed to use that. It does beat it some of the times. We can talk about why at a coffee break. But also then the efficiency of running this gets a lot better.
Excuse me.
Yes.
What's T1 and TP here? Sorry.
So T1 is the time it takes to run. I guess I took that part of the slide out. T1 is the amount of time it took on one core to run, and TP is the amount of time it took on P cores to run. So it gives you the speed up. And then the efficiency is the speed up divided by the number of cores you threw at it. So an efficiency of 1 means that you're not losing anything due to overhead necessarily. And so Monday is quite a bit more efficient at using the code as well. You throw more computing power at it, it does better. We're going to skip that for a moment, just for time. Okay, so one of the other things that we're doing for Monday and ALENS 2 is test-driven development, which is this idea and a software design principle of we're going to write our tests before we write the functions for this. We're trying to do this for all of our cases so that we do have a nice battery of unit tests, integration tests, scientific tests that test specific functions, specific combinations of functions, and the whole program as we're going through this entire process, rather than trying to rewrite them months or years later to account for things that have gone wrong. And so Monday right now is in the process of testing, and you can go type, well, you can't type C-test yet because it's done slightly differently. It'll be that way soon. Documentation. So this is one of the other issues with ALENS, is that, you know, it's all fun and games until someone else has to read your code, or you have to read your own code. And in some cases, I've seen developers act this way. This is bad. You shouldn't do this. You should comment your code, and you should do it in a way that is probably AutoGen compatible. So we use Doxygen. Right now, we don't actually have a developer and user guide. I'm collecting the information for that right now. But the idea is to have the API guide documented in the code so you can run Doxygen on it. It'll auto-generate all of your API information, but then also have a developer guide for software engineers that want to come talk to your code, and a user guide that's for someone that doesn't necessarily need to know the software engineering, but wants to use it to do something. So we're in the process of developing those right now, which then brings us sort of to just what we're going to do for ALENS. So, okay, we're going to get performance out of building on top of this Trillanos SDK package. We're making it extensible and flexible so we can add new data and new object types, et cetera, with SDK and then Monday built on top and kind of the side of it. And then the idea is how we actually get some of the flexibility is that this is all built in a way that you can use code injection from C++. So you can write your own functions in the correct namespace. It will register correctly, and you compile it against, let's say, Monday and Trillanos. So you're not actually going and modifying Trillanos or Monday. You're writing your own functions in your own source files, compiling them, and then it links against it correctly. And then have a driver on top of it that, again, you know, at some point the idea is maybe go into some sort of Python bindings for this. Right now it's in C++ still, so we're still working on that piece. So for ALENS 2, right now we're at the stage that we're working on the bookkeeping mechanism, and we're getting through testing, which Adam is taking over. I'll skip ahead somewhat. And so my main takeaways from this whole thing are just you should really, if you're developing software, you should maintain organization of all your packages. Git's great for this. You can also use the issue trackers, etc. Coding standards exist for a reason. You should probably pick a set and follow them. Testing helps out future you, so write your tests and use them. Some planning ahead of time helps you avoid pitfalls. For instance, if we had realized with ALENS that you might need non-homogeneous data types in the future, that would have solved a lot of issues had we known that then. Modularity hopefully increases our ability to do development and lowers the barrier to doing additional development on the project. Well-written documentation, makes everyone's life easier. And one of the base ideas is extension, not modification, which for ALENS and Mundi is what we're focused on, which is you want to extend code. You don't want to go inject your own code or go have to make modifications to the original source code. You really want to write your own code and not have to touch what was already written. And so I think with that, I'll sort of end with the idea that, a lot of us software developers are working on similar things and would love to talk more at length sometime about the different projects that we're working on and see what can and cannot be shared between us. And so with that, I'd like to thank everyone sort of on the project. And I guess I ran out of time. So thank you.
Okay, right. Okay. I think we have time for like 1 or 2 questions. We have a coffee break after this. So anything else? Everyone really wants coffee. Did you?
I'd be curious, like, to produce these testing and scaling graphs, kind of how automated that process is. Like, is that a one-time thing you did to make the plot for the paper kind of thing? Or is that, like, do you have a way of continuously tracking performance? And that's not something I figured out how to do. So.
That is an amazing question, because essentially we ran into this exact problem trying to reproduce a previous performance graph and couldn't necessarily do it. So we are, yeah. Yeah. So we're working on how to do that right now. I have some ideas of how to get performance testing in, but it's going to have to come in terms of, that's why I mentioned in the testing, having something like a scientific test that say you have an examples directory that runs, having something there that you can just keep track of the performance when you're running your integration tests. To check various pieces of that. So you can have it spit out what the performance is of the different pieces. You can scale it up with something like Jube or one of these automated benching frameworks. I haven't figured out how to do it yet. My sort of stream of consciousness idea is hook that up in some way to the Jenkins build so that if you run Jenkins, maybe there is a module that runs it afterwards or something that you can then go submit some test jobs to do the performance. Robert, you got some insight on Jube?
Talk to Giro about Jube because he's sort of our Jube guy.
I have.
And 2, no, not through Jenkins, but you could make a simple Slurm submission script thing through Jube that would basically scale up.
Yeah.
And then generate the graph on the fly, and
I know in
just
Jube
run it whenever you feel like it.
In Jube, you can make it do the benchmarking. It's just how to automate that.
Great. Any other questions? One in the back. Yeah.
Yeah.
Thank you. This idea of trying to do regression testing, but on performance, is a broader question. And it actually might be a good thing to talk about over coffee, but it's hard. And
yeah,
I'd love to have. I'm trying to do it myself, and it would be great to try to figure out how even to establish this, because I don't think the community has actually come to any idea about how to do this, even in the most, you know, law pack, lin pack types of situations.
Yeah, I think in many cases, what I've seen is someone goes, runs the benchmark, generates the figure for the paper, and then moves on. And then you have someone come along 2 years later and tries to repeat the same thing and gets a completely different answer because it turns out that maybe some things weren't kept the same. It was linked against a different library. We've gone through this recently with those graphs that I showed. So yeah, I think it would be interesting to have further discussion on that.
Great. Okay. Coffee break time until 4, and then we'll be back here for our final talk of day 1 of FWAM. Thank you.